Hello, I am Maarten Blaauw and I'm going to talk about 8-step models. In this talk, we assume that you already know about radiocarbon dates, how they are measured, what their errors are, how we calibrate them. And for example, that you understand that where a calibrated distribution is higher, that is that those calendar ages are more likely for that radiocarbon date. We'll start looking at basic 8-step models and then we move on to Bayesian 8-step models. The animations that you see, most of them can be downloaded either from my website or from Vimeo or YouTube. Some of the slides also have some blue R code, and if you want to, you can put that code into R to get results for yourself. Before we start looking at 8-step models themselves, let's step back a little bit and think about what paleo data tell us. So imagine here that we have a conceptual forward model where here this curve here is climate, temperature. Yeah? Sometimes it's cold and sometimes it gets a bit warmer. And that temperature then steers the vegetation, for example, in green and the ice in white. And the sediment that's accumulating in any depression, for example an ocean or a lake, reflects the color of it reflects how much vegetation there is in this case. Yeah? And then thousands of years later we come back and we sample a core from this deposit, and from the proxies, for example the color, we then reconstruct what the vegetation has been, and from that we then try to reconstruct the climate, how it has changed. Now, 8-step models are based on dates, on dated depths, and in many cases you see these 8-step models as depths on the vertical scale and then the ages on the horizontal scale. This differs a bit between software approaches. In this case we've got dates all the way back to around 600-700 centimeters depth, but you can imagine that there might be some depth below here which might not be dated. So if you want an age model for that, we have to extrapolate, which can be quite dangerous. Now, if you want to produce an age-depth model for this dataset, we can go, for example, using a basic model. We can simply connect the dots. Simply draw straight lines between the neighboring dots. And that's your classic linear interpolation, which used to be the most popular model for a long time. You see here we are extrapolating. This one here has some quite abrupt change in accumulation rate at one of the dates, and that might not be very realistic. So you could decide to then kick out that date as an outlier and then produce your 8-step model that way, so it's a bit more smooth. Or you can imagine a hiatus, so the site has been accumulating quite straight, quite linearly, then something happened which caused a gap in the record, and that gap lasts for a good few thousand years, and after that the site starts accumulating again at a faster rate. Seems quite a likely model in this case. If you do that, we can then also assume, instead of linear interpolation, linear regression between those different sets. Or we can use a, say, higher order polynomial. And that could quite quickly go wildly wrong because there could be some weird changes in accumulation rate there. One likely model is that of a smooth spline because it looks quite smooth and natural as opposed to these very straight linear models. But in this case we've got a reversal in accumulation, which is like going backwards in time, and that is a very unlikely thing. So you would like a model to not cause age reversals, because in most sites that's a very unlikely thing to happen. And we'll see later that Bayesian models many of them are made to exactly avoid that type of reversals. can also then use a smooth spline and then hiatus again. Why not? Yeah. And each of these assumptions will get you a different H-step model. So the assumptions are quite important. Now, how do we go about measuring or estimating the uncertainty of a model? We do that for classical H-step modeling by randomly choosing a single age from any calibrated distribution, a single age where a more likely calibrated distribution or more higher calibrated distribution is a more likely age. Sample that for each of the dates and then draw a curve through those sampled points. And then we repeat that process, perhaps 1,000 times or so. Then we end up with 1,000 H-depth models, 1,000 models that translate depths to ages, to point estimates of ages. Now, even if we have an undated depth, where there's no date, we can use those models to produce age estimates for those undated depths anyway. For example, 100 centimeters depth here, we have 1,000 age estimates for that undated depth. That's an age depth model with a degree of uncertainty. Now the model itself, so we don't only worry about estimating the uncertainty of the dated levels, we also worry about the model itself. For example, in this case, this straight line, which used to be the most common model and very popular. Straight line has a very peculiar feature that the further away from a date you are, the more precise your model becomes if you do this sampling of the calibrated dates. Which is really weird, right? The fewer dates you have, the more precise your model becomes. And the further away you go from a dated level, the more precise it becomes. That's what that model does, and it seems like a very strange thing to do, but that's because it's a straight line, which is probably a very unrealistic model. Instead, you would want to have something where the model deviates from a straight line, and the less information you have, the more it can deviate. And that's the type of thing that Bayesian models such as Oxcal's P-sequence or Bcron or Bcron do. Another thing that Bayesian H-depth models often do is that of only going forward in time to disallow any age reversals. And that's a very useful thing to do, and it's very easy to defend. And it actually, by doing that, it removes outlying dates, and it also gets some really good and precise models. So it's a really good thing to do. Now, I've mentioned basic H-depth models and Bayesian ones. And if you look at how many citations the different papers describing those models get, I think you get some interesting patterns. If you look to our left, we've got generic calibration programs, Calib, which has been online for a long time and first came out in 1986. And that's got a few hundred citations per year, but then has plateaued off. And since the late 1990s, Oxcal has taken over. So it's an online as well software, and it has become really the go-to tool to calibrate our radiocarbon dates. As for H-depth models, so models that are for cores where you want to produce depth to age models. Again, in red, we've got some classical models that became quite popular in say since around 2010, including CLAM, but has since plateaued off since around 2015, and instead Bayesian age models have really taken over. Bacon, Bcron, and the P-sequence in Oxcal. So now the community has really embraced the Bayesian age models, and they're far more popular now than the classical ones. So that's good. Now, Oxcal, the P-sequence in Oxcal, what it does, it mimics, in a way, drops of water falling into a bucket, and that's how the site accumulates. And there's a value k, a parameter, which you can set to be very small drops or bigger drops. So the user can set to a degree how the site accumulates. Then we've also got Bcron, where there's no user definable settings mostly, and there you have the different dates connected by expanding blobs, a bit like a string of sausages. And then there's also Bacon, which is it divides a core into many different sections, and each of those sections is assumed to have accumulated linearly. It's perhaps not a very realistic assumption to make, but the model itself looks quite flexible. Now, the accumulation rate is based on the dates, but also on prior information. We can tell the model that a site is not very likely to have accumulated very fast or very slow. Instead, we have based on looking at many different sites, we have sort of a default prior accumulation rate. And the same is true for the memory, which is how fast accumulation rate can change over the core. We've also made a new software which can deal with LED to 10 ages, and it uses the raw data from the LED to 10 ages and looks at the whole profile together, and then uses the same Bacon model to come with a new HDAT model that takes into account the uncertainties involved with LED to 10 dating. Now, there's not just one HDAT model that comes out of a Bayesian approach. It's a whole family of iterations, of thousands or millions of iterations. And it's very important not to just use then one of those HDAT models or just the average, but use them all. Yeah, and you can use grayscales to then show bits where we are very sure about what happened when with our depths, and there also are bits where we are less sure about our chronological information. And we can plot depth against age, but we can also use the proxies that we measured, our pollen, our pollution, or whatever it is, plot them against time, where more secure sections are darker than less secure sections. Now the accumulation rate for Bacon, the default is 20 years per centimeters, so it's actually sedimentation times, but this prior can be changed. Because in different sites, in different oceanic sites or older sites with more compression, there could be you could expect different rates, so you can adapt your prior to that. Bacon will generally look at the initial data and do a quick check to see if the 20 year per centimeter default seems to be a correct assumption, or if it could better be adapted. And then if that's the case, it will suggest a different accumulation rate. But you can also provide your own prior values. Then there's an MCMC process which uses millions of iterations, sometimes 5, sometimes 50 million of iterations, where it then combines this prior information on accumulation rate and also its variability, its memory. It combines that information with the new data, with the dates, to update our information about your site, about how it has accumulated. So it learns from combining the prior information with the new data and then gets you the HDAP model. So the memory is how fast our site could have changed in accumulation rate. That's a beta distribution, but could be between 0 and 1. If it's very close to 0, then there's very little memory and the accumulation can change quite a bit between one depth to the other one. But if the memory is very close to 1, then there's a large, say it's almost constant. And you can play around with that. To finalize, if we compare classical HDAP models versus the now more popular Bayesian ones, classical HDAP models are really fast. So within a second, you can have your model. Yeah? They also look conveniently precise, even or especially at low dating densities. So that sounds good. Bayesian models, on the other hand, are slower. They take minutes to run, and they also seem to have larger uncertainties, so they're more pessimistic. Classical models, trouble is that we have shown through simulations that the precision that these classical models give you is often illusionary. They're not really good. and there could be large offsets between the truth and what the models show. Bayesian models, on the other hand, although they sometimes are quite wide uncertainties, they're really highly accurate, and the precision estimates that they give you are often much more realistic than the ones that classical models give you. With classical models, it doesn't really matter how many dates you put into your site. More dates do not really increase your precision, which seems strange. On the other hand, with Bayesian models, each additional date that you enter will teach you more about the site. So it actually will make use of this extra information to increase the precision. With classical models, outliers can be a disaster. They really can be really problematic, and outliers do happen. Whereas in Bayesian models like Bcron, and the P sequence, they really they handle outliers really well. They can deal with up to say 50% outliers and still produce reasonable models. So classical models, they're fast and everything, they're precise and they remain popular, but they're really not well suited to their task. So please try to not use them, even if they give you very precise and quick answers. Bayesian models, on the other hand, they really outperform classical models, not only at high dating densities, but also, and perhaps especially, at lower dating densities, because there the model assumptions themselves become more important. So to summarize, it's really your best bet is to go for Bayesian H-step models, be they Bcron, or Oxcal type H models. And that's both for radiocarbon dates, but also if you want to use lead to 10 dates or other types of dates. Thank you.